Well, remember, when we're concentrating on columns, so think about these as the columns. And our first column will be answered here. We use those scalars. So this is going to be lambda times the first column plus 0 times the second, which is just lambda times v1. And the second one is going to be 1 times v1 plus lambda times v2. Again, I'm using lambda and 0 as the scalars for these two columns for the first column. I'm using 1 and lambda as the scalars for the second column. Well, you're absorbing that. Clean up over here. Looking at first columns, once I get my A v1 has to be lambda times v1. And that actually makes me happy. That's exactly the eigenvector-eigenvalue relation. And then what's new for this one is that second column. A times, right over here. So that's going to take a little bit of work to figure out. Okay, so for this one, that works out exactly like we wanted to. So A is, or lambda is the eigenvalue, and V is the corresponding eigenvector. This one is a little bit weird. I'm going to work with this a little bit. So I'm going to collect all the V2s on that side of the equation. And I want to factor out the V2 on the left. With that trick we talked about earlier today. Is to get the dimensions to work out, I have to sneak in a times 1, the matrix times 1. Now I can factor out. So we get A minus lambda I times V2 is V1. So let me put this, we're all, you might not see it yet, but we are almost there. Same trick here. Because I can think about V1 as being in the null space of A minus lambda I. And then watch this. If I take V2 and multiply by A minus lambda I, what do I get? And then, if I multiply both of these by A minus lambda I again, well, this is A minus lambda I squared V2. then what's a minus lambda I times v1? It is 0. So v2 is in the null space of a minus lambda I squared. So for that, we'll do some examples, but that's the trick for finding the v2. So v1 needs to be in the null space of a minus lambda I. Which essentially just says v1 is the eigenvector for lambda. And then it's doing a little bit of algebra with the next piece, is v2 has to be in the null space of a minus lambda I squared. In order for that s to be invertible, is v2 can't be in the null space of a minus lambda I. Let's write out the general directions. So to factor in A as an SJS inverse, J is going to be almost a diagonal matrix. Lambda is on the diagonal. So the first column of S is going to be an eigenvalue for lambda.
Eigenvector.
Eigenvector. In other words, it's going to be in the null space of a minus lambda. And then for the second column of S, you're going to pick a V2 that's in the null space of a minus lambda I squared. And you have to be careful, is this condition make sure S is so let's go through the example we started this section with. Start with this. Subtract off the main diagonal. Don't worry too much about copying this over because we did all this part already. So work this out, get that lambda equals 3 twice. And then, a couple things. So we know the structure of J already. 3103. Plug lambda equals 3 into this. -1, -1, 1, 1. this is our a minus 3I. We've just pre-subtracted the x and the y to both sides. So we're trying to find something that's in the null space of this. So can you give me an x, y that works here? 1. So I've got my first column of S already. So all this is straightforward. You've got lambda equals 3 as an eigenvalue. Its corresponding eigenvector is 1, 1, and that makes the first column of S. And that second column is going to be a little bit different. For the second column, I have to do a minus lambda I squared, and then pick something in that null space. This is the new stuff, because we have to do a minus 3I squared.